Hello, my name is Bob Norm. This is part 3 of a 3-part presentation on how to use Labview for PID control and evaluating a motor, building a motor model, and building sub-VIs. In previous discussions, we showed how to build a motor model, and it looks like this. You can review that if you wish. There's a control panel for it. This part is going to focus on feedback control. So what I've done is I've broken our DC input that used to run directly from here to the motor, and then we had open loop control. Now I've inserted a PID, so we have proportional, integral, and derivative inputs, and they're scaled. So here's a integrator, a differentiator, and this is just a straight scalar. So we're going to compare the input against the feedback, and the feedback occurs through this shift register that's been inserted into the while loop of the PID. So initially we start at 0 and we wrap around and feed it back in. So after our initial state, we're going to be using the shift register instead of the 0 value. I've also wired in the initialization and some initial conditions with time steps once again. I probably could have used this initial condition. It doesn't really matter. PID control loops are typically set up where you crank up the proportional component and look for a sustained oscillation. This is a Nicholas-Ziegler method. So what we do is we go ahead and turn it on, and I'm going to release initialization. There's some overshoot, but it's not sustained. I did learn that at about 28 we'll get to a sustained oscillation. So you can see it right there, and then as I decrease it a couple of notches, it's a damped response, and going up to 28 it's sustained, and if I go up to 30 we'll see that it starts to grow again. So I'm going to determine that 28 is the period of interest. Let's take a look at the step again. There it is. And I can see that there's a time period of 1, 2, 3, 4 per second, or this is 250 milliseconds is the period. There's equations that you can find on the internet that describe this. It's pretty well documented. Here's a paper that I found, and they show some of the coefficients for PID control. This will have a little bit of overshoot, but KC was our 28 value of 28. That's a critical point. So we'll take 0.6 of that, half of the time constant for TI, and 1/8 for the derivative. So if we plug those values in, we'll get 16.8, 14, and 0.3125. 0.03125. So let's go ahead and run this one. We'll flush this out once again and release, and you can see that it comes up and stabilizes pretty quickly. There's plenty of information out there on different tuning algorithms, and they would adjust the PID differently if you want to minimize your overshoot. That's not always desirable. As you can see, we're getting about 60% overview, so you need to find the PID coefficients that are suitable for your application. So I think we'll wrap it up here. Take a look. I may do a fourth part. I'm not planning on it at the moment, but if I do, it may be on how to cancel one of the poles in the motor with the 0, and we'll see if we can make it even faster. Thank you.